Hi, my name is Prashant. I am a research associate at the Center for Digitalization, AI and Society at Ashoka University. In this video, we will talk about threat modeling. Most digital systems in public life, for example, electronic voting, digital payment systems, or digital health systems, are rife with numerous complex and subtle security and privacy threats. Without a systematic approach of modeling them, discussions about their security often reduce to forceful proclamations of security and commentators talking past each other. For example, this has been famously seen in the Indian EVM security debate. In this video, we will walk through how to systematically model these threats to allow rigorous security analysis of the system and clear communication of its security guarantees and limitations. So let us jump right in with threat modeling of a reasonably complex application, electronic voting, as an example. The first step in any threat modeling exercise is a raw, informal enumeration of the threats that exist based on an intuitive understanding of the problem and known attacks. Like many such problems, the voting problem has many threats. First, there are correctness threats that a voting machine may not record the voter's vote correctly, recording, say, a button press for candidate Bob as a vote for Alice. This may be due to software bugs, but can also be due to the machine being maliciously corrupted during manufacturing or during voting. Further, even if the machine recorded the votes correctly, there remains a threat that the votes are not counted correctly during the tallying phase. On the flip side, even if all election machines and authorities behaved honestly, voters may still complain that their votes were not recorded correctly, and there is a threat that this can discredit the election. Finally, there is the threat of voters' votes getting leaked, leading to votes getting bought and sold, or voters being pressurized to vote for a given candidate. As you can perhaps imagine, such a raw enumeration of threats quickly becomes unwieldy to analyze, and there is a danger that we missed out on some attacks. To approach the problem more systematically, the first step is to provide a high-level structure to the problem. We do this by identifying various subprotocols that make up the entire system, parties involved in each subprotocol, and the input-outputs in each subprotocol. Once we have this structure, we can talk about the security properties of the system. The following protocol structure models a simple and natural verifiable voting protocol. There is a cast subprotocol to let voters cast their vote using a voting machine, a tally subprotocol to let election servers count everybody's votes, and an audit subprotocol to let an auditor verify that the election result was correct as per the voters' chosen votes. The cast protocol involves a voter VI and a voting machine M, where the voter supplies their vote little vi and the machine supplies a secret key. The cast protocol produces the voter's encrypted vote EI to be published on a public bulletin board and a receipt RI for the voter, which typically also contains the encrypted vote. The tally protocol involves the backend servers S1 to SM who take as common input the encrypted votes of all the voters and produce a final tally T using their respective secret keys. The audit protocol involves the backend servers and an auditor A where they all obtain the reported tally, the published encrypted votes, and the voter receipts as common input, and the auditor outputs a verdict where denoting whether the tally was correctly generated or not. At this point, we don't need to specify how these subprotocols work, just that they exist and follow this input-output structure. Once we have the protocol structure, the next step is to identify the system's security properties. Security properties are well-defined guarantees provided by the protocol to the honest parties even if other parties are acting dishonestly and deviating from the prescribed protocol. Most complex applications have many desirable security properties to accurately capture their full range of threats. For example, for our voting problem, one can think of a correctness property that guarantees to the voters that any manipulations to their votes would be detected, a robustness property that guarantees to the election authorities that if they behave honestly, then the election would not be deemed a failure, and a vote secrecy property which guarantees to a voter that their vote would remain a secret. Other properties can be similarly posed. Rigorous modeling of a security property requires first clearly identifying the adversarial parties for the property and then clearly defining when we would concede that the adversary has won, that is, broken the claimed security property. Note that for different security properties, different parties may need to be modeled as adversarial. For example, consider the correctness property. This is a guarantee to the voters, so the voting machine and the election servers must be considered adversarial. We denote the adversarial parties in red and mark them by an asterisk. The adversary wins if it can force the auditor to output a verdict that the result was correct even if the reported tally did not count the votes of some voter correctly. This is specified as an interaction between the honest parties and the adversarial ones. Note that we do not specify how the adversarial parties work, nor specify their inputs and outputs because they may arbitrarily deviate from any instruction we give to them to break the security property. Also, when multiple parties are adversarial, like here with both the voting machine and the election servers being adversarial, they can be arbitrarily colluding with each other. The property essentially encodes that even if all adversarial parties behave arbitrarily, the probability of them winning in this interaction is very small. Let us now model the robustness property. Here, voters are the adversarial parties, and the voting machine, the election servers, and the auditor are considered honest. The adversary wins if the adversarial voters can force the auditor to output a verdict that the result was incorrect. This models that if election authorities honestly follow the protocol, the audit should not fail. For the secrecy property, we identify the auditor and all but one election servers as the adversarial parties, modeling that the audit process should not leak the voters' votes if at least one election server is uncorrupted. The adversary's winning condition for secrecy type properties is modeled slightly differently. Here, the adversary's goal is not to force a wrong output but rather learn some secret information, say the vote of a voter. We model this by defining two similar worlds, differing only in the value of a secret variable, and consider that the adversary has won if it can distinguish between the two worlds. So, for example, in the first world, world 0, the ith voter's vote may be VI0, whereas in the second world, world 1, it could be VI1. If the adversary can distinguish between the two worlds, then it means that the protocol execution leaks some information about the votes. Note that since the voting tally inherently leaks some information about how the voters voted, secrecy holds only if the total tallies T0 and T1 in the two worlds are the same. Therefore, we define that the adversary wins if the tallies in the two worlds are the same, but the adversary can still identify which of the two worlds he is in. Hopefully, you can appreciate that a systematically developed threat model allows clear identification of the security guarantees provided by the system and the threats still remaining. For example, the secrecy property protects against an external adversary such as the auditor and the backend servers, but it does not protect against the voting machines. Therefore, if the voting machine gets compromised, such a system can still be used to learn the voters' votes. One can also see clearly if the threat model needs to be weakened in case a desired property is unachievable. For example, the correctness requirement that all manipulations must be detected may be too expensive to achieve. Typically, the election audit processes are designed to efficiently catch any large-scale manipulations enough to change the election winner and may not detect a few manipulations. To capture this, the adversary's winning condition could require it to make more than a certain number of manipulations and then go undetected during audit. Depending on the perceived threat and the practical constraints, the threat model can be appropriately tweaked. Finally, once the threat model is in place, the next steps are A. Protocol design, that is coming up with the concrete protocol steps for each party corresponding to each of the identified subprotocols, and B. Security proofs, that is proving that the proposed concrete protocol achieves the claimed security properties. We will hopefully discuss these issues in a future video.